Yeah, so today I'm going to talk about WebAssembly. Pretty short overview, so it should be like 5 minutes maybe. um, right. So typically WebAssembly, you're kind of thinking front end stuff, which is what it was made for. I'm going to talk a little bit more about how WebAssembly could be used on the back end, right? Which is kind of a different take on it. I thought it was kind of interesting, so I just kind of pitched an idea, and he's like, "Okay, go for it." So I'm going to give a good overview of WebAssembly, kind of dive into some of the features of it, and then focus mostly on the safety aspects of WebAssembly. You can go pretty deep. I don't want to keep you here for 3 hours, so just keep it high level. So just to start it off, when you're talking about running WebAssembly in the back end, it actually is a thing you can do today because Google Chrome has V8 as its JavaScript engine, so does Node.js. And actually, there's projects going on to get OpenJDK, which is the leading Java distribution, is planning on using V8 for the scripting API as well. So you could actually do it, well, if you're on Node, you could do it today. If you're on Java, probably, I don't know, it's like Java 12 or something like that, might have that. So even if you're not on any of those backends, there's plenty of, there's at least one WebAssembly implementation written in C. You could easily pull that into as a library into just about any other language environment you had. So with that, we're going to talk a little bit about WebAssembly as for backends. And is it a good idea? Is it a bad idea? I'll kind of leave that up for you to decide. I'm just going to kind of lay out the idea and see what you think, and it's kind of a discussion starting point. So WebAssembly, it's really fast. There's actually some really compelling benchmarks out there. So it'll take an algorithm, write it in JavaScript, write it again in C, and compile down to WebAssembly, and yeah, you get like 20x, 30x performance improvement. It's pretty compelling benchmarks out there. So it's made its case for the web browser. And one of the ways that it gets those benchmarks is it focuses on being really, really low-level language. It's basically an abstraction over the CPU. It's not high level at all. It's really as low as it can get without being totally tied to the CPU. And so web browsers, of course, target mobile phones, tablets, laptops, etc. And so as such, WebAssembly is focused on the CPUs that run on those platforms. So there's two main CPUs, architectures, ISAs. There's ARM, which is kind of the RISC architecture, kind of simplified, and then Intel x86, x86-54, which is a lot bigger, more complex. Their WebAssembly is aimed at targeting both of them. And these are pretty divergent ideas for microprocessors. WebAssembly is kind of this abstraction over both of them. And it's so much of an abstraction that people are talking about running WebAssembly even on GPUs, which is an entirely different architecture altogether. So it really is intended on being an abstraction over CPUs. When you do load a WebAssembly module, well, you don't load it, the web browser does. One of the first things that the code will do is compile it. So it goes through an explicit compilation step. Initially, the initial implementations of WebAssembly, several of them would actually ahead of time compile it right down to machine code. I think I'm kind of getting the feeling that Firefox and Chrome have kind of left that idea and they're going to more of a just-in-time compiled model. But either way, it's the implementation is free to ahead of time compile it right to machine code, which is kind of a compelling aspect of it, actually. So if someone comes to you and says, "Oh, I'm writing WebAssembly," it's probably not true. They're usually compiling down to WebAssembly. You're usually going to write sort of higher level language like Rust or C or C++ or Fortran or COBOL, whatever your flavor is. But in terms of languages you can choose from, you typically don't choose from ones that have a garbage collector. So JVM, Python, Ruby, all those things are typically not options. It comes down to basically, those languages have a garbage collector, and you don't want to ship the garbage collector with it. There's no reason why you can't ship a garbage collector with these, or there's no reason why you can't implement a garbage collector. I mean, so WebAssembly views memory just like the CPU views memory. The CPU views it as just one linear block of memory, and you can to run C or C++, you actually have to implement an allocator. Same thing you do with C and C++, or regular CPUs on the operating system. And you can do the same thing. You can implement a garbage collector, like a JVM, and you can absolutely implement the entire JVM for WebAssembly. It's just a recompilation step. In fact, people do this with just about every language. The trouble is you actually have to download the entire environment every time you load a page. So it's like kind of doing like a Java update every time you load google.com. Yeah, not a great user experience. WebAssembly views, in terms of memory, most CPUs divide memory into two parts. There's the program memory and the data memory. WebAssembly, it's a pretty sharp divide. So in the data memory, you absolutely use raw pointers. There's not a whole lot of data types in WebAssembly, and you use integers for pointers, and they just dereference memory like you do in C, C++, etc. However, in terms of program memory, where on like x86 you can jump to an arbitrary memory location, like for instance in C you have function pointers. Those are basically jumping to an arbitrary memory location. You actually can't do that in WebAssembly. You have to use like what's called a table. So they have concept to deal with these things, but this is kind of where the safety aspects of WebAssembly start appearing. They disallow things that have caused corruption and security problems and other platforms. And these kind of safety features are built pretty deeply into WebAssembly from the core, from the start. Like the design is built from the beginning to be able to be formally verified. Right. So again, WebAssembly is meant to be an abstraction over CPUs, a very low-level abstraction over CPUs, and doesn't have the features of a language. So you compare that with, say, the JVM bytecode. There's opcodes in the JVM for allocating an object, accessing a field, different opcode for accessing a static property. It's very oriented around Java, and you can, of course, build lots of other languages on it, they have, but they're all they have to have some commonalities. It's kind of a little bit constraining in terms of languages. On the other hand, WebAssembly, they did add concepts on top of what a CPU uses, but all the concepts they add are purely for the safety reasons. So like they have functions, modules, memories, things like that. And so for instance, a WebAssembly memory, like every module has a single block of linear memory they can access, like we talked before. And you can grow that if you run out of memory, or if you're really frugal, you can actually release memory. So you can grow and shrink this memory. But if you access or if you dereference a pointer outside of that memory, it'll cause a crash. And WebAssembly execution will just totally crash, and the host environment can handle that. So in this sense, the sense that we've talked about so far, WebAssembly is pretty contained. Like if an error happens in a module, it's totally contained to that one module. It can't corrupt the memory of a module next to it. It can't corrupt the host environment either. It's totally sandboxed. A single module is going to contain just your basic ideas, right? So functions are basically your exports, right? So it's where the code resides. You can call these functions kind of like you do in JavaScript or C. And then, of course, you can import functions as well. And you can also import variables. So we're going to go over a quick example of calling a WebAssembly function, so say written in C, from JavaScript, from the host environment. Right? So if you want to do this, it's pretty straightforward. You just call it like any old JavaScript function. Super easy, as long as you can kind of fit into the numeric types. So you can really only pass or return integers or floating points, which is a pretty big constraint. Usually you want to do like strings, arrays, objects, something. So you're pretty much always stuck into passing or writing a whole bunch of wrapper code, right? So if you want to, that does something like allocating memory inside the module. Let's go to the next slide. We have an example right here. So this example is for the C standard library function strlen, which of course calculates the length of a string, because in C we don't store the length, we just calculate it every time. So this is all JavaScript. So if you're going to write wrapper code, you'd write it in JavaScript. Actually, it's TypeScript. I like types. So the red box there is highlighting what the goal is, or you can call it right there, but the rest of it is just wrapper code. So the first line would be we allocate some memory here. Okay, so that is the literal C standard library function malloc, right? And WebAssembly doesn't provide these allocators. Again, the C standard library includes an allocator. You can like JE-malloc or whatever. But since it takes and returns just numeric data types, it's totally fine. We can call it. No wrapper code needed. But we need to call malloc so we can allocate memory in the WebAssembly environment. So this is getting kind of clunky if you think about it, right? And then you have to go copy the data from the JavaScript heap space into the WebAssembly environment. So it's pretty clunky, and of course you got to free the memory at the end, which is add all that in. So in a quick example of the other direction, let's call the host environment. Call a JavaScript function from C. So if you look on the right, there's a C header, function header for calling the environment. If you look at the C side, it's a char star or char pointer. And on the left is JavaScript, and that's integer, because that's how we represent pointers. It's just pointer, integer, right? And technically, we could just reach into the memory location and just print it out, except for it would come out as a whole bunch of numbers. We want to print it out so it looks like a string, so I actually have to do some Utf-8 decoding, right? So if you look at this, this is kind of terrible. You don't actually want to do this. So luckily enough, there's plenty of wrapper generators. If you've been following WebAssembly from for its origins and into its infancy and where it is today, you'll know plenty about Emscripten. People have been using Emscripten as a framework for compiling whatever C++ down into JavaScript in the early days, and now it's to WebAssembly as well. The Rust language has been really wonderful, actually, at keeping up with WebAssembly. So their tooling is actually developing at a pretty good rate. But one of the big takeaways I want you to take from these couple of slides is that WebAssembly is really, really good at being fast and not really good at doing anything else. You can run code really, really fast, but you can't really, you can't access the network, you can't access file system, you can't even access a timer, which is great for security people, or because you mean no timing attacks. But if you want to, it's not so great for application developers, right? But it's nice though, because it's purely a sandboxed API, like it's a whitelist-based API. So you don't have anything in a WebAssembly module that I didn't explicitly give to you. In fact, I had to write the wrapper code and literally import it into your module before you could actually use it. So it's, from a security posture, it's actually kind of a neat way to think about it. And this is where I started thinking oh, well, let's try this. What if we use this on the back end, right? So I kind of poked around, and one of the big things you run into, so I'm sure there's mostly back-end developers here, so I don't have to explain the back end too much. But on the front end, you're only working with one user at a time, right? On the back end, you got to deal with multi-tenancy, right? Not always. You can set your system up so you don't have to, but a lot of us have to deal with this, right? So in the front end, where we're worried about cross-site scripting and such, in the back end, you also have to worry that every request is isolated from every other request. This goes pretty deep, and it affects just about anything. And so one of the big reactions was when you tell a back-end developer that you want to run third-party code inside of their trusted servers, you're like, no, we're not doing that, right? And there's been things like webhooks that have come up. I would say more recently, Amazon Lambda, well, the whole serverless thing, so all of the Azure functions, Google Cloud functions. One of the big use cases for those is actually callbacks and integration like that. I know I've used it in the past for implementing APIs that want to execute customer code inside of a trusted environment. It actually works fairly well. It generally just uses the network and operating system file permissions to kind of guard the system and keep it isolated. So it's not as limited as WebAssembly, but it functions mostly the same way. I would say where it breaks down is if you have a really high fan-out model where, say, you've got like one function, or one web request that ends up in like 20, 30, 100, 200 Lambda calls. That gets not only expensive from the money side, but also latency. Each of those Lambda calls can take a while, right? Especially if you hit a cold start, right? So I think where WebAssembly comes in is like what if we could do like the Lambda thing, like the in-process callback, like we'll do it in process instead of on a different machine, right? That's where it starts getting kind of interesting, right? And like I think we've all kind of become used to seeing something like this, right? It probably doesn't even matter what language you work in. You've seen something like this. I mean, even C# people have seen this. They just call it different things, right? But almost every language that we work in these days has pretty rich APIs based on the idea of passing functions. And like, there's a whole bunch of applications that this is really cracked open. Like, there's actually really compelling reasons, really compelling things it's already done for us in terms of APIs, like collection APIs, atomic data structures. It's actually pretty crucial for that. Reactive streams. I don't know if you've heard of Quick Check, but it's actually a really cool thing. You should totally Google it if you haven't heard of it. It probably wouldn't even be possible without first-class functions. So it's really revolutionized the way we've done programming today. So I think it really is worth looking into, can we do this for web APIs? It is rather compelling. But one of the big reasons why we haven't, of course, is so far, our web APIs have been based on the idea of passing values from, over the network, right? You hit a network boundary, you have to serialize whatever message you're going to send. So that's kind of where it breaks down, is you don't really want to send code. Well, WebAssembly, that's code, we can serialize it, right? But then it gets a little, that's kind of where the talk comes in, right? So I know I've written APIs that look like this. It's basically, you want to do some filters and some maps, and so you end up implementing this like whole bunch of different options on your URL query parameters, and it's pretty tiresome. You do this once, you do it twice, and you're like, I'm not doing it again. This is so much work. And it's so error prone. So of course, GraphQL came in, and that's kind of where they're more on the map step of that, but they also, like the filter step, I think is more punted towards the back end still. But I think there's a lot of room for, like, what if we added first-class functions to GraphQL, something like that. I think that's a pretty compelling use case, right? But so just like, it's kind of what if we could send a post request? Like, well, I guess you'd want to send a GET request in this case, and not really REST. But what if you could do this, right? It'd be kind of interesting, right? So what could we create? What could the APIs of the future look like, right? It's kind of an interesting thing to think about until you realize we've actually been doing this for decades. So like the Spark Python API, they've been sending functions. Of course, this one is a string. It says age is greater than 21, but that really is a function. I mean, it's a DSL, right? And they have to compile it. So you have to do the work of creating this language and compiling it down. And then the next distributed system over does the same thing. They do it a little bit differently, right? Same thing with Cassandra, CQL. I don't know why I chose Cassandra, because SQL is probably more well known. And it's the same thing, right? I mean, and the best part is the CQL versus SQL. They do it a little bit differently. You have to look at the documentation every time. So we've been generating all these DSLs. They do it slightly differently. It'd be nice to standardize on passing actual code. Maybe, I don't know. It could help. Something outside of DSLs, so Spark again, but looking at the Scala APIs. This is kind of interesting to think about, but they actually do pass code. If you notice, they're using actual Lambda functions, right? And it's because they have they get the jar sitting on both sides. They're running a JVM on both sides. So in one sense, they actually are passing code, which is kind of interesting to think about. And this is all getting pretty difficult, right? And I think one of the things I want to get to is none of this is probably doesn't lend itself well to open APIs, especially forcing like a JVM on both sides or JavaScript on both sides, which is another point I was going to bring up. You can do the same thing with JavaScript as well. Like you can easily paste JavaScript into a JSON message, but you have to run JavaScript on the back end, which I don't know if you want to do that. So it comes down to it, WebAssembly could actually be a great way of serializing code. So I think it's worth looking into. So I'm going to go through a couple examples of, here's like a really naive way, like how might you send code over the line? So we're going to start off with C code. The basic way to do it is to start off with writing C code into a file, and then you set it, so you'd be doing this on the client side, right? And you just compile it with GCC or Clang or whatever your favorite C compiler is, and link it up into a WebAssembly binary and post it across the other side, and they can execute over there. Of course, I mean, that's super awkward because when you're running GCC in a browser, it's kind of like running JVM in a browser. So maybe we should be sending the C source code, the plain text source code. It's probably a little more scalable of a model. Don't know. So what I'm thinking is maybe, I don't know why I came back to GraphQL here, but whatever. It's on my mind, I guess. Let's say there's a GraphQL function, or actually be like an operation, like a RPC or something like that, right? It takes a string instead of a first-class function, and then you just literally paste in C code, right? That could work. I don't know. We're just kind of tossing out ideas at this point. So then, if just to run with this for a little bit, and in the back end, you might have a little template sit around. You just kind of paste that code in there, and voila, compile, run, execute, boom, done. Like, this could actually work. It might work. Of course, I just kind of threw in that compile step on the back end. We already established that running WebAssembly is safe. We didn't talk about compilation, but it's not a horrible problem. It's not insurmountable because we can just compile the compiler down to WebAssembly and voila, that's safe too, right? So I think there's some of the transitive property continues there. And so at this point, I've been totally assuming that WebAssembly is completely safe. I think there are some holes in that argument. I think when it comes down to, like one of the big holes is you can, at least in the multi-tenant system, right? You can execute code for too long. It's like unbounded execution. So that currently is definitely a hole with this whole thing. But it wouldn't, I looked into the V8 source code. It doesn't seem too difficult to add like a time-bound execution. Of course, you got to convince people it's worth adding. So maybe that's what this talk is for. Maybe we can start this conversation. Anyway, that was just kind of a total aside. But we have to talk about what language you might want to send this code in, right? I've been using C as an example so far. That could work. I don't know if people really want to be writing C because we're talking about a lot of web developers and memory management. I don't know. So yeah, C is kind of seen as being hard. WebAssembly, obviously, we just mentioned several slides ago. It's for robots, right? So probably don't want to use any of those directly. However, I did run into this thing called assembly script. If you're familiar with TypeScript, if you can compile an assembly script program, it will also run through the TypeScript compiler, which means you can target literally both JavaScript and WebAssembly. So that's starting to get really interesting. Like, so yeah, we need to consider, like, is this actually a useful technology? I think it probably would be, right? We could start sending JSON and then start sending first-class functions in there, right? That's kind of an interesting idea. So something to think about. So just to kind of recap what we've gone over today, I think we've established that WebAssembly is mostly a safe place to run untrusted code. I think so. Functional APIs, I think we've definitely established that they provide a lot of value for us today, and I think web APIs probably provide the same value there too. And then kind of the to-do note here is we got to figure out a good serialization code format. Assembly script might be it, so looking into. But anyway, I want to leave you all with this message. Just go talk to each other, maybe see if this can become a real thing. I think it's interesting to think about, see what we can do. So if you're looking for more information, we've got webassembly.org. I actually found out this idea, this whole slide, this talk, it's not even new. They thought of it like years ago, so I thought it was like a brand new idea. It's not. So there's tons of information up on webassembly.org. Also, the Rust programming language. If you do anything with WebAssembly, Rust always comes up because they've got a really great toolchain for it, and it's improving at a really rapid pace too. They're putting a lot of effort into that. Finally, you've been a great crowd. Thanks for listening. Oh, right, you can contact me. There's my Twitter and email address. Right, I started working at KenSci yesterday. It's a new startup in town. It's kind of fun, machine learning. So you can contact me and talk to me about whatever you want to talk about. Thanks.